All right. So today is Tuesday, March 16th. We are working on daily quiz number 14 for the attendance. It's simple questions compared to the last one. This is much simpler. So I hope everybody answers and scores all the points there. In terms of homework 7 is due tonight, and homework 8 has been posted on Piazza, and it's due Tuesday of next week. In terms of studio, you guys have been working on Studio 4, which is due tomorrow, and Studio 5 is due March 31st. So you have 2 Wednesdays to work on Studio 5. However, it has 3 tasks. One is on a decoder, a couple of them are for encoders, or I think is the other way around. 2 of them are on decoders, one of them is for an encoder. So I suggest that you guys start early on Studio 5 tasks. Note that today is a Tuesday, so we are going to have TA held help sessions in the evening, 6 to 8 and then 8 to 10. So utilize those 4 hours to make progress on the studios. We are going to continue our discussion about the muxes. So today we are going to see a very interesting topic, at least it's interesting to me, in that we are going to see if we can synthesize any logic function. So you give me any logic function and I will synthesize it using a mux. The size of the mux may be different, but any logic function, I will be able to synthesize it using a mux. So what I'll do is I'll run through an example logic function, and the logic function over here is expressed in a canonical sum of products form in shorthand. And I'm going to synthesize the same logic function using an 8:1 mux, a 4:1 mux, and a 2:1 mux. Same function. So let's see if we can do that using the 8:1 mux first. The function f depends on a, b, and c, and as they have been laid out in this shorthand notation, it looks like our a is the most significant input and c is the least significant input for those specific minterm numbers. Right? These are the 4 minterms that constitute this logic function. Now, if we switch around the order of the inputs, then we'll have to adjust the minterm numbers, but that's how the function is given to us. A is most significant, C is least significant input, minterms are 0, 1, 3, and 7. So what I'll do is I will go to a truth table first, and filling out a truth table given the shorthand canonical sum of products form should be pretty straightforward, because you are going to enter a 1 at row 0, row 1, row 3, and row 7. Those are the locations in which you have a 1. So row 0 is a 1, row 1 is a 1, everything else, so 3 is a 1 and 7 is a 1, and everything else is a 0, right? So I hope you guys agree with that. That's simply a conversion between 2 forms, truth table and canonical sum of products. Now once you have that, let's try to take a look at some statements here that we can make about the truth table. When a is 0, b is 0, c is 0, I want f to be a 1. Now, can I get that through an 8:1 mux? You see that 0, 0, 0 entry is way at the top of the mux, right? And it's an 8:1 mux, so of course I need 3 select lines for this, and those select lines are 1, 2, and 3. So next question is, what should I connect to my select lines, and what should I connect to my inputs, the data inputs to the mux? Well, if I want the truth table to transition to a 8:1 synthesis, I can simply copy the output column here, paste it right there, and attach it to my inputs, the data inputs of my mux. And in order for this to work, I would have to match up my inputs and the select lines over here. So suppose I have the select lines as S2, S1, S0. 3 select lines in that specific order. S2 is your most significant select. So when S2 is 0 and S1 is 0 and S0 is 0, 1 will go through, right? That's exactly what you wanted for your function. So your output will become the logic function itself, and this will work if I attach ABC, the 3 inputs to my logic function, as the select lines in that specific order. And then the output column here directly transitions over there. Now you can quickly check this, right? So if A was 1, B was 0, C was 0, what would be F? Well, A is 1, B is 0, C is 0. That means S2 is 1, the other two are 0. So that would correspond to this entry. That means 0 is being selected through this mux. And if you look at this, this is exactly what we want based on the truth table. So synthesizing a logic function of 3 variables with a 8:1 mux is very straightforward. All you have to do is take that last column in your truth table and then attach that as the data inputs to your 8:1 mux, and then lay out your select lines as the inputs to the logic function in that specific order, in the same as order as they have been listed for that minterm numbers. Pretty straightforward. You guys are getting this. It's simple enough at this point. Yeah. All right. So logic function to an 8:1 mux. Well, the logic function being 3 input variable to an 8:1 mux was pretty straightforward. Now let us see if we can do the same logic function. We can synthesize the same logic function using a 2:1 mux. I've drawn the 2:1 mux symbol over here, where I have 2 data inputs, 1 select line and 1 output. I want to synthesize the same function. So what should I do? Well, one systematic approach to synthesizing using muxes is to use Shannon's expansion theorem. Very systematic approach. And I'll walk you through the theorem here. The first step that we need to do is write out the logic function in its complete canonical sum of products form, complete one. So I'm going to do that first. Let's say F. So CSOP, complete, for F. That's your first step. And that would give me F equals, I have 3 input, all right, 3 inputs, ABC, right? So I'm going to say ABC or ABC or ABC or ABC, and then put ands in the middle, and then complement variables as and when needed. So for the first one, I have minterm 0, everything gets complemented. Minterm 1, the first 2 get complemented. 3, 0, 1, 1. The last one, everything is straightforward, right? Everything is in true form. So that's your first step. Next, because I have a 2:1 mux, can you guys tell me how many select lines I need here? How many select inputs? Question mark. 1, right? So of course I need to select 1 between 2 inputs. I need 1 variable to be my select variable. In the previous example, I had 3 select inputs, A, B, C. Now I have a choice. I can either have A or B or C to work as my select input. So I'm going to invite you guys to do that selection. Pick one out of those 3. Pick one, and whoever A. All right. Andrew says A, so we'll go with A. A, B, C as select variable. Andrew picked A. After that selection, we are going to try to rewrite the function while expanding it with respect to the select variable a. How does that look like? I'm going to say f equals a complement multiplied by a certain logic function, or a with some other logic function. And the reason why I'm picking a complement and a over here is because of that choice of one select variable being a. Could have been b, could have been c. Now I need to figure out what goes here and what goes here, such that this f matches this f, which of course matches that f, right? So let's try to figure out what goes in the first one, and then we'll do the second one. All right, so a complement, right? So there is a complement. Oh, sorry. There's a complement here, there's a complement here, there's a complement here. All right, so all those things, all those remaining products are going to go in the first square brackets. So I'm going to put in, let's see, maybe in red, b complement or c complement, or b complement and c, or b and c. Next, so I've taken care of this guy, and this guy, right? The only thing that is left is over here, a and b and c, and that will go nicely in the second square bracket. I only need to put b and c over here. Now, if you look at this, you may be able to simplify this, right? So this you may be able to simplify. So what I'll do is I am going to copy this and maybe paste it over here and try to simplify it over here. So in order to simplify, what can I do here? I can maybe take a b complement out of the first two terms. So if I pick b complement as the common factor from the first two terms, I've got c complement or c, which will give me a 1, or b and c, right? And then this simplifies to b complement or b and c, which equals b complement or c. Right. If you factor out c, let's see, if Andrew says factor out c, which let's try if that works. So c, if you factor out c from the last two terms here, you will get b complement or b complement and c complement, which will give you c or b complement and c complement, which will be c or b complement, right? So both of these, as you can see, they match each other. So the simplest form here is going to be the same. Now, if you are scratching your head, how was he able to go from here to here? I used property 11D from Boolean algebra properties, and you can check this later if you want. All right, so we have simplified it. We no longer have all this complicated one. We simply have b complement or c. So let's go back and say all of this is simplifies to b complement or c, right? And this one is sort of the simplest, right? Like it's already simple. Now, in order for me to synthesize this using the 2:1 mux, my select variable was a, so that becomes my select line. When a is a 0, b complement or c should go through, and when a is a 1, b and c should go through. So I'm going to say this guy is going to be b complement or c, and the second one is b and c, and this is my f. And as you can see here, it is very important to note that this one is your top input coming from that guy, and this one is your bottom input. Whatever that would have been, it goes at the bottom. And of course your A was your select variable. This is so simple. I'm starting to see why you like muxes. Yeah, see, I told you. You will appreciate it a little bit. Hold on, like I think the the climax is still there. Like the awe factor is still remaining. This is not all about it. But now you need B complement or C, and what was that? Right. So I have a 2:1 mux. It's going to be simpler than an 8:1 mux. Uh, so I still need some logic gates, right? So I need something to not this, something to or this, something to and this. So in fact, what I'll do is I will draw a little bit more detailed symbol here. Select line doesn't change. I got a or at the beginning. And then I had an and over there. Two inputs to that, two inputs to that. I see. Let's put 0 here, 1 here, and this would be A, this would be F, this would be B complement, this would be C, this would be B, this would be C, right? So you have got some logic gates here going into a 2:1 mux, and you are able to synthesize the same logic function. Now it's also useful to see if it checks out, if it matches the truth table from earlier or not. So before I do that, I just want to make notes here that this one is going to be your bottom input. This is your top input to the mux. Now we can pick any arbitrary sequence. So for example, I can say when A is 0, what would be F, right? So when A is 0, the truth table, the logic express, the 2:1 mux design says when A is 0, F should be B complement or C. Hold on, you guys are wait. We are getting there. So the 2:1 mux synthesis says if A is 0, F should be B complement or C, right? So let's try to see if this actually matches the truth table. Where is A0? Well, A is 0 for the first 4 rows, right? That's where A is 0. And if you look at the relationship between B, C, and F, you can see F is 0 only when B is a 1 and C is a 0, right? So based on that, you can say F is B complement or C. Or you could do the whole thing, right? You could say 1 here, 1 here, 1 here, which means B complement and C complement, or B complement and C, or B and C, which will simplify again to B complement or C. And if you do the same thing for the next 4, where A is 1, A is 1, F should be B and C, right? So the 2:1 mux synthesis that we had here matches the truth table. So we were able to check that satisfies truth table. TT. All right. Questions about how do you synthesize a logic function using 8:1 mux and then the same function using a 2:1 mux? Now, when I said climax, I really meant that this can get a little bit, because if you can expand once, you can expand twice, you can expand thrice, right? So you can apply Shannon's expansion theorem within a Shannon's expansion theorem. You could apply that Shannon expansion theorem for this guy and this guy, and you can keep going down, right? You will have more select lines in that case. All right, let's see how that works. And we'll do that by going to a 4:1 mux. So same function now using a 4:1 mux. So I invite you guys to pick the select lines. I would need 2 of them. So you can pick something else, the A and C, A and B, B. All right. So I think Peter's B came in first. So I'll pick B and then C. All right. Pick B and C. All right. We'll settle with B and C. So what I'll do is I will take this guy from before, because I have to start again, right? I have to start at the beginning. That's my canonical sum of products form complete expression. And Peter says, let's do B first. All right, so we have pick 1 out of A, B, and C as select variable, as most significant select variable. And Peter picked B. So I'm going to do this expansion using B as my select variable. So let's see, F equals, I'm going to do the skeleton first, where I have B complement or B. And then I need to figure out what goes into those square brackets. So let's see, for B complement, I would have this term, that's it, those 2 terms, right? So I've got A complement and C complement, or A complement and C over there. Those are for B complement. And then for the next 2, I have B there and B there. So I've got, what do I write here? A complement and C, or A and C, right? Now, I could go on and simplify. Actually, let's go on and simplify, because I think we will be able to learn better things with that. So let's see. Let's go on and simplify this. So what does this simplify to? No. Cannot simplify to 1. Oh, A complement, right? Yeah. And then what does this simplify to? You have A, so C is common, and then you've got A complement or A. Those 2 will cancel out, and you get C here, right? You guys see that? B complement, A complement, or B and C, right? So far you know we have done the select. Let's see, we've done the select here in B, and then the simplest was A complement over here, C complement over here. So if we were to synthesize it using a 2:1 mux with B as the select variable, this would be the top input and this would be the bottom input. And clearly now I hope you see that there is a difference in cost, right? So if you chose A as the select variable, you had to put in some logic gates, which was more costly. So depending on which input you pick as the select variable, it will change the cost of your implementation. So that's the first thing to note. Second thing to note is we cannot stop here because we need to use a 2:1 mux. We just figured out one of the select variables here. I need to do a Shannon's expansion within each of these expressions. So we are going to do pick another one. Pick another select variable, but our choice is now limited, right? We cannot use B now. I have A and C. So between A and C, did we settle on which one we were using? Let's see. C. All right. So we are picking C next. Bennett picks C. Let's do F now. So F is B complement, C complement, or C, or B, C complement, or C. Now, all of this, you see, all of this, let's me use maybe green. All of this has to match all of this. Now, if that has to match, and then of course the other one too, right? All of this will have to match all of that. So what should I put in here and here? A complement does not have a C complement. A complement doesn't have a C. So where will it go? Will it go here or will it go here? Oh no, can't do it. Because if it is nowhere, then how are you going to match these two both? That's right. It goes in both. So if you find something that does not belong directly to one of them, it will go in both. Right? So you have a complement here as well as A here, A complement here. And you can see that if you simplify this guy, you would actually get A complement, right? That's right. It's literally before we simplify. Yes. But in some cases, you might not see this step, right? You might just have a situation where you don't have somewhere to put it. So if you don't have somewhere to put it, it'll go in both. Because the complement version or the true version, they both will cancel out. All right. Next, what should go here and what should go here? This has to match this guy. So what goes here and then what goes here? So this has to match this, right? So 0 and a 1. That's right. So if I put a 0 in here and a 1 in here, then I'm matching this to this. There is a 1 with the C and nothing with the C complement. You guys okay with this so far? So this becomes my 4:1 mux synthesis, in which B is my most significant B is my most significant select, C is my least significant select, with 4 inputs to the mux being A complement, 0, and a 1. We can just put it over here, right? So B, Peter chose B, Bennett chose C. Then when we expanded, we had A complement, what did we have next? 0 and a 1. In that specific order. And this will be your F. This will be your 4:1 mux. And if you want to label it completely, then we can say this is my S1, this is my S0, this is 0, 0, this is 0, 1, this is 1, 0, this is 1, 1, right? And we can go ahead and check this. Let's see, based on this particular sketch, say B is 0 and C is 1. What is F? Why not do C and tie it together? Why not C and tie it together? So C is my select variable here, right? So there's a 0 there, there's a 1 there. Instead of 0 and 1, could you do C? What happened? Why is this guy not? Okay. Hold on. C. C is 0, C is 1. Yes, you could do that. Yes, yes. Because over here, C is a 0 and C is a 1 there, right? So you could do that as well. But that would work only in this situation. I'm trying to talk about a process that would apply to all situations. All right, so let's come back and let's see if we can check this. B is 0 and C is 1. What is F? Based on this diagram. So B is 0 and C is 1 is right there. So A complement goes through. So F is A complement, right? And let's see if that satisfies the truth table. Oh my gosh, why do... All right. Let's try to highlight certain situations here. One is B is 0, C is 1. B is 0, C is 1. 0 became 1, 1 became 0. A complement. You guys see that? And if you did this for all the cases, they would match up exactly, provided the Shannon's expansion was applied correctly. So same expression using 8:1, that was the simplest. Then 2:1 mux, had to apply Shannon's expansion once, had to pick a expansion variable. Picking an expansion variable could lead to a simple implementation or a little bit more complex. And then we talked about 4:1 mux, where we had two expansion variables. One was the most significant, the other was the least significant. So that became our topmost input to the mux, and then this one, and then this one, and then this was the bottommost input to the 4:1 mux. What changes when using POS with a mux? So I would work with SOP forms in the mux. I would literally convert POS forms into SOP and then work from there. All right, and then if you try to verify this for all the conditions, no more. Yeah, since you guys didn't like that at all. All right, let's try to look at some other interesting things we can do with the mux. So here the task is synthesize a 2-input AND gate using a 2:1 mux. So let's say we are trying to do something like this. We are trying to do an AND gate, 2 inputs, and let's say our inputs are A and B, and our output is C. Right, 2-input AND gate. We are trying to synthesize this using a 2-input 2:1 mux. So I would start with this canonical sum of product form. So I would say C equals A and B. Next, if I have a 2:1 mux, then of course I have a select variable. So somebody who has not picked a select variable yet, can you pick a select variable? You have choice of A or B. Expansion variable or select variable. Someone choose A. All right, Drew chooses A. Big expansion variable between A and B, and Drew picked A. how A and B are, I'm not able to see it. How is it going to be any different? A and B are so far at the same level. Like there's no need to prefer one to the other. I wanted B. All right, we can. You wanted B. I thought, Andrew, you said someone choose A. All right. Drew has picked A. We'll go with A. C equals A complement. Then I need to figure out what goes there. A followed by what goes there. So what should go here? Followed by what should go here. Such that this C matches that C. What should go in the first one? Zero, right. No A complement term there. What should go in the second one? B. Perfect. A and B, right? Good. And now we are ready to sketch it. So let's see. I've got a 2:1 mux here with one select line. My select line was A. When A is a 0, 0 goes through. When A is a 1, B goes through. This would be my C. So synthesizing AND gate using a 2:1 mux. All right, questions about this example? All right, Shini, if you are curious, sounds unnecessary. If you are curious about doing the second case, the expansion variable as B, then all you got to do is switch these two, right? This sounds so much easier than the last two lectures. Well, all right. Let's reverse the question. Yes, absolutely you can. Let's reverse the question and say you already have the mux designed. There's the 2:1 mux, and the goal over here is to find the relationship between the output F and the inputs A and B. So what do you guys say? One way to do this, there are many ways to figuring out that relationship. One way to do it is when writing statements, right? So that would be when A is 0, what is F? And then when A is 1, what is F? Right. Bennett has that's another, the second way, right? So based on this particular 2:1 mux diagram, there are two statements we can make, right? So when A is a 0, F is what? B complement. And when A is a 1, F is B. So when A is 0, you are getting the complement of B, and when A is 1, you are getting the true form of B. So it's like the equality detector, exclusive NOR. So that's one way of doing this. The other way of doing it is by using Shannon's expansion, but in reverse, right? So you do f equals a complement and something, or a and something, right? Because a was the expansion variable here. And in the first one, you would put in the top input, and in the second one, you would put in the bottom input. So here you would get b complement, or here you would get b. This would simply be a complement and b complement, or a and b, which is a exclusive NOR b. Yes, you guys were right. All right. So that's as far as we are going to talk about Shannon's expansion theorem, and you know, trying to synthesize logic functions using muxes and taking advantage of a very systematic approach to this, which is your Shannon's expansion theorem. We still have demuxes to talk about before we get into the latch. So just a mux summary here. Muxes are data switches. They are allowing one of the data inputs to go through based on the select inputs. They can be used to switch one or more bits. They can route incoming data to a selected output. We will see a diagram in just a minute where you can use a multiplexer and a demultiplexer together to select between one source and one destination. And if you look at the opposite, right, the demux, if you are selecting with a mux, you are distributing data using a demux. It is going to be exactly the same concept, but reverse operation. So let's take a look at the demux here. Demultiplexer, going to be the opposite of mux. So earlier we were selecting one from many. Now you are routing one input to one of many outputs depending on what you select. So a schematic or a logic symbol will help. I'm going to put a 1:4 demux here. So one input comes in, it can go to one of 4 outputs depending on 2 select inputs. So this is my input I, for example. My outputs are, let's say, y0, y1, y2, y3. My 2 select lines are S1 and S0. And when S1 and S0 are 0, 0, input goes here. 0, 1 goes here. 1, 0 goes here. 1, 1 goes here. So you can write the statements here about that, the description. S1, S0, if you have them as 0, 0, that implies that Y0 is going to be equal to the input. And S1, S0, 0, 1, Y1 is going to equal I. And then, of course, the other 2 situations. So the input is being routed to one of the output lines. So it's like distributing data. Now, all of this we can actually put it into a logic diagram format. We can as we designed a 2:1 mux based on the truth table for it, we can actually do the same thing for the demux. This is your 1:4 demux. One input being demuxed into 4 outputs. Muxes seem similar to encoders, demuxes like decoders. They are similarities, but their purpose is to change the code altogether. Right? Demux like decoder. We will actually see an example where we can use a decoder to function as a demux. That's coming up in just a bit. Let's see. After, let's do. Here is my square paper right here. So let's try to build this 1:4 demux. For this, I would need 4 AND gates. So let me put 4 AND gates first. 1, 2, 3, and 4. Followed by outputs going here, 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 and here. Next, I'm going to have the input I going into all of them. So I goes to all 4 AND gates. And then I can have the select lines. So for example, I can have 2 select lines go in to each of those AND gates. For the first one, my input will be S complement, S1 complement, and S0 complement. For the next one, it will be S1 complement and S0. For the next one, it will be S1, S0 complement. And the last one, it will be S1 and S0. 0, 1, 0, 1, 0, 0, 1, 1. Right. Now, all I have to do is label the outputs. So if you see this, if S1 is 0 and S0 is 0, I will go through to Y0, Y1, Y2, Y3. You see that? So we can say, all right, what would happen if S1 equals 0, S0 equals 0? What would happen then? Well, Y0 will equal I and everything else will equal 0. You see that? So this is how you can build a 1:4 demux, but this is simply using AND gates. All right, there has been some discussion in the chat box. Let me keep track of it. Muxus seem okay. You would just make one high and then we'll be decoding. I think that's what I was thinking too. All right, let's take a look at that. This is a block diagram showing you that you can use a multiplexer to select between many sources, use a bus to go through to a destination, and then at the destination you may have to choose from one of the many destination points. So you would use select lines for the destination to demux whatever you got at your through the multiplexer. So a block diagram view of this selection and distribution is shown over here. You have a mux to select between 26 sources. So can you guys please help me? How many lines are there? No, not a lot. No. So there are these are 26 sources. How many lines do you need to select? 5, right? That's it. So if I have 5, then I can select between 32 sources. I just have 26 here. Is the screen frozen for you guys? I feel like the screen has frozen. All right, now I think it's coming back. So you have all these select lines over here to pick one out of 26, go through the bus, and then you have another 5 select lines to distribute it to one of the 26 destinations, right? For example, if I want to go from C to A, what would I need to do? I would need to pick C 0 0 0 1 1, maybe not 1 1, maybe 1 0. And then over here I would need to pick A, so 0 0 0 0 0, right? Is it because you need 2n? Yes, exactly right. So if you have n select lines, you can select between 2 raised to n data sources. All right. This is what I was talking about when I mentioned that you can do this demultiplexing using a decoder. So there are two block diagrams here. On the left, you have a generic decoder where everything is sort of active high. You have your data of your source coming in to the enable pin. You have 3 select lines to do the selection for the demux, so that this source can be routed or distributed to one of the 8 destinations. Right? So 1 to 8 demux is what we are looking at. Now you can do this with a standard 74x138 3 to 8 decoder. Let's try to see how that works. G2B is connected to ground. That's good, right? I don't need to worry about that. That's enabled. So let me that's hardwired to enable. I don't need to worry about that. The same thing applies for even G1, right? G1 is hardwired to +5. It's always going to be enabled. Now G2A, which is actually a active low enable, I'm using that pin for my active low source data. No reason. Like I could have used G2B here, or I could have gone active high over there. I'm just doing this over here to show that it can be used as a 1:8 demux. These 3 are your select lines, A, B, and C. You have 8 active low outputs. So let's try to see. You have 2 options here, right? So if this is 0 and this is 1, you have 2 options. Along with those 2 options, you have 8 options to do the selection here. So let's pick a certain combination. Let's say we have a 1 connected here, a 1 connected here, and a 0 connected here. And let us try to see what happens for the case that this is a 0. Source data is a 0. What would you see where? So first of all, is the decoder enabled or disabled? Enabled, right? So this is connected to high, this is connected to low, this is connected to low, so this is enabled. So that would mean that it will actually do the decoding job of 110. What is 110? This is of course your least significant input. So you should actually read it as 011, which is decimal 3, right? So this guy would be active. That guy would be active, means this is a 0, everything else is a 1. You can see that 0 went to a 0. You were able to distribute that source to one of the 8 possibilities depending on the select lines. And again, we can also talk about this with the other case. When it is a 1, what would happen then? Let's 1 as well. If this is a 1, what would happen? Is it enabled or disabled? Disabled, right? So there everything is a 1, right? Exactly. Everything is a 1. But more importantly, your source is the same as the destination. Everything is 1. That's right. So this kind of design would work as a 1:8 demux, but now you are using a decoder to do that distribution. All right, let me stop over here. talk about a couple of things.